somehow, right? And then bulk modulus works the same way. Okay, so now we can look at a table and say, okay, what's the Young's modulus? Let's focus on the second column in gigapascals. So if we look at, let's say, brass, 102, Young's modulus of brass, 102 gigapascals. Take some of them and put them down. Aluminum, 69. Okay, and then we can look at iron, 210. And then steel, about 200. So iron steel is about the same. So the harder, the higher this is, the harder it is to stretch and compress that material. So aluminum is the easiest. Yes, it is true, right? We already know it's more stretchable, bendable. But they have here, other than metals, they have even wood. Okay, now if we look at the bulk modulus, this is B. Well, we also have the bulk modulus for the same similar metals, right? Aluminum, 680, so it's about 70. Aluminum is 70 gigapascal. So it's Young's modulus and bulk modulus are the same. In other words, this one, if you're trying to compress the aluminum, versus this one, you're just stretching it in one direction. You see? So the numbers are similar, right? And then if we look at brass, 108. Slightly bigger than that. So far we see these numbers are similar to these, but slightly larger. And then we have iron, 58 to 107. Oh, that's smaller, huh? That's kind of weird because it doesn't fit this pattern. That's why I like looking at tables and kind of comparing and seeing if there is there a pattern, and if there's not, what can we learn from that? This one says that it's easier to compress an iron volumetrically than it is to compress it linearly or stretch it linearly. So this is compressing, expanding volumetrically. Oh, so that one was weird. And then you got steel, 139, depending on the kind of steel, 159. So again, for steel, it's the same thing too. So even that's easier than that. But so far, those ones that they gave us were the bulk modulus of the solid materials and the Young's modulus of solid, and the bulk modulus of solid. So now over here, when we're relying on the velocity of sound in the solid, why are we using the Young's modulus of the solid versus the bulk modulus? Are we saying that when you make a sound wave in a solid, it travels mainly one directionally? In other words, if we use the bulk modulus of the solid, it would mean the sound wave is traveling more spherically in the solid, right, everywhere. If you use the Young's modulus, it would mean like you're hitting this, you know, or this ruler means traveling one directionally, you know. So I think this one could be applied to different scenarios. If we hit like a train track and the sound wave travels along the train track in one direction, right? Then we would use this. But if I wanted to do the sound wave traveling, let's say something happens, an earthquake happens on the Earth, and the sound waves travel through the interior of the Earth three-dimensionally, right? When an earthquake happens, I might have to use the bulk modulus of the solid if it's traveling spherically, right? Then we would use these numbers. Okay.
So it depends on how the wave is traveling, whether you...
Yeah, if it's one is called a spherically wave, and the other one is called a linear plane wave. Linear plane wave or spherically propagating wave. So now we could also look at, let's see here, bulk modulus of liquids and gases. Bulk modulus of acetone, benzene, ethyl alcohol, kerosene, mercury, seawater, water. Interesting, huh? So those are the bulk modulus of the if we kind of look at the extremes, what's the smallest one of this? Let's see, the smallest one is about acetone, benzene, acetone, so the alcohols. And they are also gigapascals, right? So if we compare them to the bulk modulus of the solids, they're much easier to compress and stretch volumetrically, right? And then benzene, so of course numbers should make sense because liquids are more kind of fluidy, right? So easier to compress and stretch versus the solids are, right? On the other hand, mercury is 28.5. Does that make sense? Pretty high, huh? It's kind of very solid-like, right? The density even is high. So mercury, yeah, it makes sense. Very thick fluid. And then seawater is 2.34. Water, 2.15. Why is seawater more?
Different.
More salt content?
Yes.
So what does that do? Salt content makes it harder to stretch? I guess, yeah. And then the other things are about the same, huh? So, okay. Now what's left is to do the gases. So should gases be even smaller?
Yes.
So this table doesn't give us, okay. The bulk modulus of a gas is highly dependent on the process that you do to stretch and compress the gas. Is it isovolumic or isobaric, which we're going to cover when we go to thermodynamics, right? The liquids and solids, it doesn't matter if you do it at constant pressure or constant volume. You don't have to distinguish. So that's why they say here EV for an isothermal process, EV Kp for an isentropic process, right? Trying to find a table. Diamond keeps coming up because it's very stiff. Okay, it's got a couple. There's a lot of math there, huh? Partial derivatives. Wow. Oh, well, if you look at this table for the what was the other one that we used? It was the 1.4 times the pressure in the air over the density of the air, right? They gave us the 330, I think it was. Well, if we use the bulk modulus of air for an adiabatic process, that is 1.4 times the pressure in the air, but not the isothermal one. So in other words, velocity travels in the air by an adiabatic compression and expansion. Adiabatic compression and expansion, not an isothermal one. Adiabatic means no heat losses. Isothermal means constant temperature. You see? So the propagation of sound is more adiabatically done. So 1.42, right? If you put here 1.42 kilopascals, oh, sorry, 142 kilopascals divided by the density in the air, you're gonna get the 331 number, that middle one, right? I'm trying to find the bulk modulus of helium because one of the things I want to show you is why is it when you inhale helium, your voice changes, right? Because the velocity of sound in helium is faster than the velocity of sound in air. So make this something a little practical. Bulk modulus of helium, let's see if we can find that. Oh, okay, so it's actually a problem here online. So the problem gives it to us. The bulk modulus for helium is 101 times 10 to the 5th. So that would be like 101 kilopascals. Also, it would be kind of like wasn't that the same as the bulk modulus for air isothermally, that we said it's not that one? That one would be like that. 101 kilopascals. Velocity of sound in helium. not 331. Square root of, so then we're going to put 1.01 times 10 to the 5th. 1.01 times 10 to the 5th divided by the density of helium, which is going to be a lot less dense than air is 1.3, right? This is 0.179, much less dense than air, right? Let's see what that gives us. (751.2 meters per second). Now I'm going to divide that by 331 because that's the base number for the Bach modulus. I think these ones, I think we're doing it for 0 Celsius. So then divide by 331. .27. So the answer is, yeah, it's not that easy, huh? It's 1, the answer. Is that do these things give the answers? I want to see if I'm right. Now that I solved it, oh, I gotta create an account. Ah, shucks. So yeah, that would be the one. So if the Bostef sound in helium is twice as much, the frequency that you're going to generate with your vocal cords are going to be twice as much. So as soon as you inhale it, yeah, the resonant frequencies, which is chapter 18, interference, diffraction, and standing waves, the resonant frequencies that your trachea creates when helium is going up and down is going to be twice as much at least. Right? So you're gonna sound very high pitch. If you keep inhaling that, yeah, you can do like a high alto sound, mezzo soprano. Okay, so now from this, one of the things I wanted you to learn is how do the units work out? What is the meaning of these equations? And then how does this equation, the 1 plus t over 273, how does that relate to the bulk modulus equation? And you can kind of see that this applies to that when it's only in air. And the temperature dependence is because the bulk moduluses that we saw were all temperature dependent. These numbers are only true at the temperature of whatever they're giving. I don't know what temperature it is, 0 Celsius, right? So all these, the Young's modulus is not too much temperature dependent because solids don't change their properties much. But the gases ones, that we saw, this bulk modulus of air, highly temperature dependent. So when the temperature changes, the bulk modulus is going to change, and then that's going to fiddle with this. And so that's what this equation comes in, is it says, okay, when the temperature changes, this is what happens to the velocity of sound in the air. Okay, let's do a couple of problems with that. So let's say there is a lightning that strikes. A lightning happens. So you see a lightning, let's say here. Let's say this is -4. Okay, so then this is lightning comes and strikes here, and let's say the distance from here to here is something like 10 miles. Okay, and we have here who are 50 miles away. So how long after seeing the lightning will you hear the thunder? Right? Assume the temperature on the ground is 20 Celsius, but it decreases by 2 Celsius for every 1 mile of elevation. Okay, so what's going to happen? The lightning pretty much comes to you pretty immediately, right? How would we calculate how long it takes the lightning for you to see the lightning? How would we calculate that? The distance that the light has to travel is what? Well, if the lightning is kind of flashing straight down, you're kind of seeing it either after it hits the ground or maybe while it's in the air. When it's making contact with the air particles, it's giving off light already, right? So it's kind of coming to you either from its origin or somewhere here or somewhere from the ground. But it really doesn't matter because light is traveling so fast. It doesn't really matter, is it from the middle or is it from the top or is it from here? It's still going to take about the same time. So we could do a quick calculation for how long it takes the light to come to you from the ground, let's say, or from the cloud. It doesn't matter. So the time for the light to arrive would be what? Well, if it's coming from there, right? Then what's that time going to be? So the distance is going to be 50 squared plus 10 squared square root divided by the speed of light. 3 times 10 to the 8 meters per second, right?
Would we have to change the miles to meters?
Huh?
Would we have to change the miles to meters?
Oh, yeah. Okay, change that to meters. So what would that be? Times 1 mile is 1,600, I think 1,609 meters to be exact. 1.609, right?
Yeah.
Okay, so that gives you the right? 0.273 milliseconds. Very short time. So you pretty much see the light right away after after it occurs. That's when you see it, right? 0.273 after it occurs. That's millisecond. Very, very small. Okay. How about the sound wave? Then the sound wave is created here, right? Then it goes spherically. It spreads, right? So then it's coming through you like that, right? So you're seeing it from there. So the distance, the time for the sound wave to reach you is going to be what? That distance divided by the time. But the temperature over there is colder than here. So the sound wave initially is traveling slower, right? Then it's speeding up, right? So it's going to be an integration problem, right?
Yeah.
So what's going to be the, let's see here, the time is going to be equal to what? Let's go like this. Velocity of sound is dx dt. So then this is going to be 331.2 or 1 plus t over 273.15 square root, right? That's equal to the distance that it travels over the time, right? Dx. So I'm saying the distance that it travels is from here to here, a small increment. So let's draw a picture here. If the thunder is happening here, I'm going to put my axis. Let me see here. Should I put my axis here? Put my coordinate here, x, y. Distance here is going to be I'm trying to come up with a general equation for, let's see here, at a certain position to have here from here to here. It's going to be x plus the height. So the distance here is going to be what? Square root of x squared plus h squared, right? So the distance this way is going to be always this distance squared plus this distance squared, right? We'll call this, let's say, I don't like calling it d because when we take the differential of it, it becomes dd. What's another symbol? Z, let's call it.